Okay, I hope this time it will work. I supposed to give this talk yesterday, but for some problem with internet, I was not able to. So I hope this time it will work. Uh, this talk about generalization of valuation domain, and the title of the talk on N pseudo valuation domain. This is by Ayman Badawi and my colleague and friend David Anderson. And I will get to it. I bring you back to 1978. There are two papers by Hedstrom and Houston. They introduce a pseudo valuation domain. And the way you think of pseudo valuation domain, generalization of valuation domain. And what is a pseudo valuation domain? So you, as usual, you let R to be an integral domain and a quotient field K. And if every prime ideal, let's call it Q, satisfy this condition, which is whenever you have xy in a Q for some xy in K, then x in a Q or y in a Q. If every prime ideal Q of R satisfy this condition, then R, we call it pseudo valuation domain. There are many algebraists studied or maybe still studying this class of domains. This is a generalization of a valuation domain. And all of us, either undergraduate or graduate, we studied valuation domain. And let me remind you, there are many definitions. This is the one I use. R is called integral domain with a quotient field K. Then R is called a valuation domain if x in R or x, the inverse of x in R for every x in K, whereas K, remember, is the quotient field of R. Okay, so pseudo valuation domain, generalization of valuation domain. Okay, in 1991, Dan Anderson and Muhammad Zafrullah, they introduced in this paper here, they introduced almost valuation domain. And let me remind you with the definition. You let R to be an integral domain with a quotient field K. Then R is called almost valuation domain if for every non-zero x in K, there exists an integer, n, here n has to be an integer, positive integer, depend on x, such that x to the n in R or x to the minus n in R for every x in K. Okay? So almost valuation domain, again, means that whenever you choose a non-zero element in the quotient field, there should exist an n, and n here depend on x. That means not necessary that the same n work for every x, where x to the n in R or x to the minus n in R. So quickly, if you let n to be 1, then it is very clear that if n equal 1, then we're going to have valuation domain, right? So it's clear almost valuation domain are generalization of valuation domain. And of course, there are many examples of almost valuation domain that are not valuation domain. For a recent paper, you can look at this paper on almost valuation and almost Bizu by Mahdu and Mimouni and others in 2015. Okay. And okay, so let me bring you back just 1 minute. Remember that pseudo valuation domain are generalization of valuation domain. In 1991, they introduced almost valuation domain. So what do you expect next is to generalize almost valuation domain, and this is in 2007 I introduced a new class of domain called on pseudo almost valuation domain. So the way you think of it, pseudo valuation domain, generalization of valuation domain, pseudo almost valuation domain, it will be a generalization of almost valuation domain. And here's the definition of pseudo almost valuation domain. You take R to be an integral domain with a quotient field K. If every prime ideal satisfy this condition, for every x in K, there should exist a positive integer n such that x to the n in Q or x to the minus n, that means the inverse of x to the n, times a is in a Q. For every a in a Q, that's what's missing here. I should add for every a, this a in a Q. If every prime ideal of R satisfy this condition, then R will be called pseudo almost valuation domain. And as I told you, it turns out by definition, if you remember the definition of almost valuation domain, then clearly almost valuation domain is a pseudo missing here almost valuation domain. Okay, yeah, so what I said here, every valuation domain, and in fact correct what I wrote, almost valuation domain and pseudo valuation domain are pseudo almost valuation domain. So pseudo almost valuation domain, generalization of pseudo valuation domain, generalization of valuation domain, generalization of almost valuation domain. Okay. So here is a new a concept that we need. Here we, as usual, we let R to be an integral domain with a quotient field K. Then I be a proper ideal of R and n bigger or equal to 1. So we fix n here. N will be bigger or equal 1 positive integer. Then I, we call it n powerful ideal if whenever x to the n, y to the n in I, for some x, y in K, then x to the n in R or y to the n in R. Okay? So n powerful ideal means that. And here we fix an n. That's crucial to follow. N is fixed. And I will be called n powerful semi-primary ideal, the same condition if whenever x to the n, y to the n in I for some x, y in K, but here we want x to the n in I or y to the n in I. So that's the difference between n powerful and n powerful semi-primary ideal. N powerful, you require that x to the n or y to the n in R, where n powerful semi-primary, I require x to the n, y to the n in I, whenever you have this condition here. And let me stop for a minute here. The concept of powerful ideal was studied by Ayman Badawi and Evan Houston in this paper in 2002. So when n equal 1, this is what called powerful ideal. So powerful ideal are just one powerful ideal. So in this paper also we generalize the concept of powerful ideal. In fact, also in that paper with Evan Houston, we studied a new class called almost pseudo-valuation domain, but I decided not to talk about it here because we already have many concepts. We have valuation, almost valuation, pseudo almost valuation. So I don't want to talk about almost pseudo valuation domain. Even in our paper is like 24 pages long in a print. We generalize also this concept. Okay? All right, so we get to what do we mean with n pseudo valuation domain. It means if every prime ideal of R satisfy this condition here. What is the condition? If you have a prime ideal I, let's call it, and you have x to the n, y to the n, and the prime ideal for some x and y in K, then x to the n has to be in I, or y to the n has to be in I. Okay? So if every prime ideal, here is what's written, and also you have to pay attention here, n pseudo valuation domain, that means we fix an n. So we fix an n, then we ask every prime ideal to be n powerful semi-primary ideal. Every prime ideal need to be n powerful semi-primary ideal. What is n powerful semi-primary ideal? You see it here. It means whenever you have x to the n, y to the n in I for some x, y in K, then x to the n has to be in I, or y to the n has to be in I. If every prime ideal of R satisfy this condition here, then R is called n pseudo valuation domain. Well, if you let n equal 1, then this is what the classical pseudo valuation domain in terms of Houston and Hedstrom, the classical papers on pseudo valuation domain. If n equal 1, then you get pseudo valuation domain, or just one pseudo valuation domain. Okay, so if you want to follow my talk, you need to know what we mean with n powerful semi-primary, and you need to know what n powerful ideal, and you need to know what we mean with n pseudo valuation domain. N pseudo valuation domain means every prime ideal of R must be n powerful semi-primary ideal. Okay, so now we're going to give you some properties. So we have this implication, and none of them is revisable. Valuation domain always means pseudo valuation. Pseudo valuation always pseudo almost. And now we have the new class that I'm talking about now, n pseudo valuation domain. And remember that here, what I mentioned here, none of these implication revisable. So that means in this paper, we gave examples of n pseudo valuation domain that are not pseudo almost valuation domain, that are not pseudo valuation domain, and that are not valuation domain. Okay, so that means what we have is a new class of integral domain. We extended these classes You have valuation, pseudo, pseudo almost. Now we have n pseudo valuation domain. And here is the example. The example is you to take R to be Q. You know, Q is the field of rational numbers, and C is the complex numbers. And this ring here is a subring of the power series C double bracket X. You can think of R as a subring of the power series C double bracket X. Here we want the constant term to be rational. Notice here the coefficient of x squared is in C, is a complex number. And also observe that we don't have x term and we don't have x cube in this ring R. And then, you know, these are things you check. Then this is not pseudo almost valuation domain, is not pseudo valuation domain, and definitely this is not also almost valuation domain. So this ring here is not this, is not this, and is not this. But you can show that this R is 4, n here is 4. Is for pseudo valuation domain. What's that mean for pseudo valuation domain? That means whenever you choose a prime ideal of this ring and you have x to the 4, y to the 4 in the prime ideal for some x and y in the quotient field of R, then x to the 4 has to be in this prime ideal, or y to the 4 has to be in prime ideal. Okay? And also observe that R is not in pseudo valuation domain for every n between 1 and 3. So the smallest one here is 4. These things you can check that. All right. Here are some properties of these n pseudo valuation domain. Here is one, and that's very nice. Remember the definition of, so I is a prime ideal and n is bigger or equal 1. You fix an n, and you assume I is n powerful semi-primary. Well, for a prime ideal, this concept is equivalent to this concept. What this means, that if you have a prime ideal, to show its n powerful semi-primary, it's only enough to show that I is n powerful ideal. Okay, remember what's I meaning, what is n powerful semi-primary? It means that whenever you have x to the n, y to the n in I, for some x and y in k, then x to the n has to be in I, or y to the n has to be in I. Where powerful, whenever you have x and y, x to the n, y to the n in I for some x, y in k, then you want to show only x to the n in R or y to the n in R. So maybe to check n powerful is easier than n powerful semi-primary for a prime ideal. Okay? For a prime ideal, to show it is n powerful semi-primary, just show it's n powerful ideal. Okay, so this is a very nice result here. And here also it tells me that if you have two prime ideals inside each, I mean one of the prime is inside a bigger one, and the bigger one is n powerful semi-primary, then the smaller one will be n powerful semi-primary. Okay? And definitely remember that from this result, it's enough to say that Q is n powerful ideal, because n powerful semi-primary or n powerful ideal are equivalent when your ideal is a prime. So the way in the street language, if the bigger prime is n powerful, then the smaller one is n powerful. So what you conclude then, you only need to show that an integral domain is an n pseudo-valuation domain. You only need to look at the maximal ideals, okay? Well, in fact, there are not many maximal ideals. Look at this result. If R is n pseudo-valuation, then R is a quasi-local domain. What does quasi-local mean? Quasi-local mean R contains only one and only one maximal ideal. Okay? So that means you only, if you're looking for n pseudo-valuation domain, you only need to look at the integral domain with exactly one maximal ideal, and you need to check if this maximal ideal is n powerful semi-primary ideal, and that's it. Why? Because if the maximal ideal is n powerful, then all other prime will be, by this result, they will be n powerful semi-primary ideal. Okay, this is what I told you, this result here, that n is powerful if and only if a maximal ideal. That's the only thing you need to check. Okay? All right. Here is the result that I isolate, but kind of interesting. This is, maybe this is the only result in this talk where R need not to be an integral domain. Let R be a commutative ring and n bigger or equal to 1. Then an ideal is n semi-primary if whenever you have x to the n, y to the n for some x, y, and r, then x to the n in I or y to the n in I. Somebody might tell me, well, you gave this definition earlier. No, the definition I gave you for n powerful, and the x and y are chosen from K, the quotient field of the integral domain R. But here I'm choosing x and y from the same ring, okay? Clearly, I mean, you can check that the radical of I has to be prime, definitely. And here is what's kind of interesting, this result. If I is n semi-primary of R, then I is n, is m for every m bigger or equal to n. So if I is the 3 semi-primary ideal of R, then I will be 4 and 5 and 6 and so on, semi-primary ideal of R. This is like isolated result, because in that paper, in fact, the first section we study this class of ideals. But in this talk, I'm not going to talk about that. Okay. All right, here is something. So if you go, why did I mention the previous result? Because here I told you if I is n semi-primary ideal, then I will be m semi-primary ideal for every m bigger or equal to n. So maybe you're going to ask the question, what about if I is n powerful semi-primary ideal? Does it mean I is m semi-primary ideal for every m here I should, m powerful semi-primary ideal for every m bigger or equal to n? So I is n powerful. Well, if n powerful, then definitely it's n semi-primary, and hence it is m semi-primary for every m bigger or equal to n by the previous result, by this result here. But what about the powerful? I is n powerful semi-primary, and you choose m bigger than n. will I stay M powerful semi-primary? The answer is no. And here we gave an example. So the answer is no. And the example, we do have an example of N powerful semi-primary that is not M semi-primary when M is bigger or equal, bigger than N. Okay? And here is the example. You can look at it, or you can look at the whole paper. All right. So what is N divided prime ideal? Well, so you have a commutative ring and you fix an N. Then a prime ideal, we call it N divided prime ideal if x to the n is a factor of p to the n, or for every x outside the prime ideal, and for every element p inside the prime ideal. X to the n is a factor of p to the n in R for every x outside the prime and for every element inside the prime. Then we call the ring n divided if every prime is n divided. Okay, here note, if n equal 1, then we already studied this class. In fact, Dobbs, David E. Dobbs, he studied divided domain, and then I generalize this to a divided ring. So if n equal 1, we already have this class, we call it divided ring, okay, in terms of Dobbs Badawi things. Okay, so it turns out that n pseudo-valuation domain are in fact n divided domain. Every n pseudo-valuation domain is n divided domain. That's a nice result. In fact, we already know if you let n equal 1, then what we have is a pseudo-valuation domain, and we already know that a pseudo-valuation domain is a divided domain. So this result is still true for n pseudo-valuation, then R is n divided. Okay? All right. Here is a nice result too. What about if your domain is root closed? What root closed mean? It means if x to the n is in R for some x in K, then x has to be in R. So, like if you want to solve polynomial x to the n equal to a, whereas a is in R, the only solution for this equation inside K is x to be in R. So you're looking for the solution of x to the n equal a inside the field K. Then this x has to be an element in R, in fact. This is what we call root closed. So if R is a pseudo-valuation domain, if and only if R is n pseudo-valuation domain. And that should be clear. It's no big deal. But so if your ring is root closed, then 3 pseudo, 4 pseudo, 5 pseudo, they are nothing but pseudo-valuation domain. Okay. Here is also another result that usually you should do, that if you choose a prime ideal in R, and then you'd look at the quotient R mod the prime ideal. If your R is an n pseudo-valuation, then this will be n pseudo-valuation. Okay, next, I mentioned this definition, but I remind you with the definition what we mean with almost valuation domain. almost valuation domain means for every x in K, there is an integer n depend on x, where x to the n in R or x to the minus n. We generalize this to what do you expect? N value. So we fix an n here is fixed. Then R, we call it valuation, n valuation, or just n valuation domain, if this is the condition, x to the n in R or x to the minus n in R. So what does that mean? It means n valuation domain are always almost valuation domain. But definitely, almost valuation domain, they do not need to be an n. And we have an example. In fact, in this paper, we answer almost, I cannot say, but whatever, we thought about, it took us a while sometime, but we end up, answering the question. We gave examples for many cases, like can we have an almost valuation that is not n valuation? Yes. In fact, we end up giving an example of an almost valuation domain that is not an n valuation domain for any n. So we generalize this concept to n valuation domain. And remember again, n valuation domain, if n equal 1, then this is nothing but the classical valuation domain. Okay, here is comment, which I just told you. I mean, like, yeah. And here are some examples, as I promised, of almost valuation, but they are not n valuation. But I just read this to you. You can read this example, but not n valuation for any positive integer n. Okay? So if you take this ring here, and this ring here, we claim that you can read it. Here are other properties, like if you have an overring and you have 1 over s in V for some s in M, I mean here, okay, now we decided that if you fix an n and you have an n pseudo valuation domain, then this n pseudo valuation domain will have only one maximal ideal M. If you have an overring, what is an overring, by the way? Is a ring, but between R and the quotient field. If you have 1 over S in V for some S in M, M is the maximal ideal of R, then V has to be n valuation domain. Well, when you see this result quickly, you come up to this one. Choose a prime ideal. Suppose P is a prime ideal that is not maximal. Then definitely this is an, localizing R at the prime ideal. It's always going to have an element 1 over S, right? So definitely you get this for free from this result, because this ring, when the prime ideal is not equal to, and that's crucial. In fact, in our case, if the prime ideal equal to M, then the localization will be just R. Is it? Yeah, definitely. Okay. I think I supposed to stop now. So I will end up with this classification of n pseudo valuation domain. So you fix an n, and we know that in order to look at the n pseudo valuation domain, then they have to have only one maximal ideal. That's what we mean a quasi-local domain. Quasi-local domain is called, we mean the domain has only one maximal ideal. Other, they call it local domain. But for me, local domain mean one maximal ideal and Noetherian. But here, I'm not saying R has to be Noetherian. So, and this I think used by Kaplansky and other. Gilmer used quasi-local, but many authors call it local. Okay, anyway, so if you have an integral domain with one maximal ideal, then the following are equivalent. Look at this. The integral closure of R has to be a pseudo-valuation with this maximal ideal. So these two conditions are equivalent. Okay. Here is some definition for what we, in fact, we use that a lot, but I try to avoid as much as I can because I already have many definition. This definition, in fact, we use it to characterize many of the things we did in the paper. Here I mention it as just in the last result. AN, what ANM means? X to the n, so our elements x to the n, such that x in k and x to the n in m. All right, that's this set. Okay, then you take, in this result, you take I to be the ideal generated. Of course, the element here, by definition, are in the ring R, in the integral domain R. So you take I to be the ideal generated by this element. Let me stop for a minute here. If you let n equal 1, then look at the definition. If n equal 1, then I is nothing but m, the maximal ideal of the integral domain R. So the interesting case when n is not 1, okay? And if n is not equal 1, then I also still maybe or maybe not equal to m. Here is the characterization. R is n pseudo valuation. This over ring, and let me remind you what's this mean. All the element in K where xi is in I. That's what this notation means. All the element in K, so this set or this over ring consists of all element in K where xi is a subset of I. Need to be n pseudo valuation domain. In fact, it's kind of interesting maybe. If n equal 1, then I will be m. And we already know R is a pseudo valuation domain if and only if this is valuation domain. So for n equal 1, this is known. But it turns out the known result also true when you go to a bigger n. All right? Okay, no time. And if you are interested in this talk, I already have this paper on my personal webpage. You can free download. You can go to this link and you go to the free download of my publication and you get the whole paper for free. All right? Okay. And I thank you.